Good afternoon, everyone. My name is Craig Yu. I'm an associate professor of computer science at George Mason University. So today I'm going to share with you some of our research on automatic generation of virtual reality scenarios and XR experiences. So before that, I want to briefly introduce my group at George Mason. So I'm leading the group on design computing and extended reality. And these days, we've seen lots of advancements in AI, emerging technologies like VR, AR. So the mission of our group is to envision what would be the future of work, entertainment, everyday life be with all these technologies. And of course, we need to come up with new computational approaches for entertainment, for work assistance, and so on. So we want to use our research efforts to envision all these possibilities. And our research domains include computer graphics, computer vision, and human-computer interaction. And we like to use techniques such as optimization, artificial intelligence, machine learning, simulation type of techniques to devise different novel tools for the purpose that I mentioned. So there are a few major domains that our group focuses on. The recent focus is on generative XR experiences. For example, we will be able to use a generative model to adapt an augmented reality storytelling experience to an outdoor environment or indoor environments that you are in. And we are able to use machine learning techniques to drive virtual assistants to be more interactive, more realistic when they interact with the users in the scene. So this is one direction we're working on. Another direction that we have been working on for a long time is computational design. So basically, we want to turn design problem from a manual process into an automated process, right? So in order for us to do that, we have to you have to mathematically formulate the design problem, right, as a mathematical problem that we could utilize computing power to automate and solve. So along this line, we are able to generate, for example, interior design layouts, work plans, workplaces, architectural layouts, and earlier on, we also worked on generating 3D models that have different desirable properties. For example, the 3D models are able to break into parts, and they can be interchangeably assembled into different shapes. So if we turn the design problem into a computational design problem, then we can utilize the power of computers to trade off between many different factors and also to achieve some very implicit goals that are not easy to achieve by human designers. So another big direction, of course, is using virtual reality for purposes like training and application. And here we are especially looking at personalized VR training, right? So you know that in virtual reality, we have complete control of everything, right? So we can control whatever events to happen. We can also very closely track the human responses to different stimuli in the virtual environments, right? So having those abilities allows us to personalize virtual reality experiences, right? So for example, we may have a computational framework underneath that would based on the data tracked from the human performance, adapts the virtual reality experience to deliver a better training, right, for that person. So we are creating different approaches that would allow this kind of experience. And finally, another domain that we work on is computational interaction. So the major idea is that we formulate the interaction mathematically such that we can analyze the interaction between the human and the tool or the computer interface in a quantitative manner. And doing that gives us ability, for example, creating interfaces or tools that are adaptive. For example, we have the adaptive wayfinding aid that will only show when the person is confused working in the virtual environment. And how do we know whether the person is confused or not? Of course, we can rely on machine learning models that are trained on classifying whether the person is feeling confused about an environment or not. And using that machine learning classifier as the driving components of the tool, then we will be able to adaptively show the assistance as needed. So along this line, we also work on some other stuff. For example, recently we also work on virtual reality-based robot teleoperation, and in this kind of scenario, AI will be super helpful, right? Because first of all, you don't, as an operator, you don't really want to do all the delicate manipulation, right? Because it's very tiring, and it's also very difficult to do if you need a high precision, right? So in that case, you can let the user give some high-level commands, right? And the computers will be able to understand the high-level intention of the user and being able to automate the low-level manipulation, right? So this is one example. We can embed AI to achieve a better human-robot collaboration. So in the following, I will give some examples of the interesting projects that we work on along these directions. But before that, I know this talk won't be too theoretical or mathematical, but I still want to show a picture like this, because I think this is really the heart of a lot of these research problems out there. So basically, if you talk about computational design or using a mathematical model to generate stuff, so I mentioned that you need to mathematically define the problem, right? So basically, based on the mathematical definition, you are defining a design space, right? And this design space has manons, has values, right? So the manons correspond, if you are talking about a minimization problem, so the manons corresponds to areas that are high costs, right? High costs means they are not good, right, in regards to the criteria that you define, right? So the goal here is to let the computer or the optimizer to locate some good values, right, which correspond to the good solutions. So if we can formulate a problem like this, and if we have an effective optimization strategy or search strategy for locating the good solutions, then we automate the design process, right? And you can see that, like, in a landscape like this, there are many good solutions that you can harvest, right? And if you just do the design manually, of course, you can still create some good designs, but probably you are only able to explore a small area of your solution space, right? But if you formulate this mathematically and you rely on the computer to automate the process, then you can possibly sample lots of good solutions in this whole design space. So that's the major idea about the computational design. And I will talk about some works that utilize this kind of framework for generating the design. So first of all, I want to talk about the virtual environment synthesis. And this is a pretty old work. And this is actually my first SIGGRAPH paper 15 years ago, around, 14 years ago. So, but I still want to briefly talk about this, because based on this, we have lots of new inspirations and ideas that lead to the new projects. So basically, this is an early project. At that time, not many people thought about generative model, but we are creative enough to formulate the interior design problem as a generative problem, right? So basically, so this is the IKEA CAD design interface where designer drag and drop the objects and make the arrangement. And if we are able to formulate the problem as an optimization problem, we can rely on the automation provided by the optimizer to sample solutions, and it's automated. So you can potentially generate lots of solutions. So the basic idea is that if you have some examples, you will be able to use some machine learning techniques to extract some common patterns that you observe from those examples, right? And after that, you'll be able to formulate an optimization problem that would generate something random, but not too random, in the sense that it should still regard the patterns that are observed from those examples. Okay, so by doing that, and of course, this is an optimization problem, and everything is very well defined. So if you have some additional considerations you want this interior design to have, for example, you want to ensure there must be a path from this door to that door, right? So you can also, as long as you can mathematically represent that, you can also incorporate such consideration into the design framework, and the optimizer will be able to respect that and generate something that has that goal in mind, right? So again, this is a stochastic process, so you can throw the optimization process multiple times to generate multiple rooms. And actually, I remember when I was at the dormitory working on this, I used to work till like, I don't know, 2 a.m., right? And then I just run the script, let it run, generate the scenes for me, right? And 8 hours later, when I woke up, so I could see like hundreds of results on my screen, and I would used to inspect. I used to inspect like which one is good, which one is not good, and if it is not good, why it is not good. So I can, use this automated process to get lots of results. Of course, that day, that time I was running this on my small laptop in the dormitory. It was like 14 years ago, so I didn't have very strong computing power. So if I run it overnight, I could only get like, a few hundred results. But these days, with the computing power that we have nowadays, I think we can instantly get a solution, right, in no time. So if you are interested, feel free to refer to our paper for more details. So this is an old work, but based on that, we keep working along this line and applying this methodology for generating different experiences, right? So I mentioned virtual reality training, right? So you know that you can use virtual reality for training people about like how to drive, how to control an airplane, and there are many different training applications associated with virtual reality these days. And we are especially interested in personalized VR training, as I mentioned. So the general idea is that in such a training, we should have two variables here. We should have two major components. First component is that we should be able to understand the user's performance, right? And virtual reality is a perfect platform for doing that, right? So for example, we can create a city simulation. We can run a pre-evaluation to let the user drive in the simulated city, right? And we can measure the driving habits of the person very well, right? So for example, does the person signal before changing the lane? Does the person pay attention to the jaywalkers on the road? So all these things, right? And I used to got blamed by my driving coach a lot when I was learning about how to drive, right? And because I make all these kind of mistakes, right? So I kind of got inspired by him, basically, about the mistakes that I made, right? And we formulate all these into the framework. So these are the things that the computer can track very easily. And on the other hand, we need to have the optimization component, right? Optimizing what? So optimizing the driving experience. And this part is also inspired by my driving coach, actually. So for example, if I was really bad at making turns, okay, so I remember my coach asked me to just make like 100 turns in this neighborhood, right? Go to this intersection, turn left, and then come again, go to this intersection, turn left, come again, until he thinks that I'm good enough, right? So using virtual reality experience, we can easily generate this kind of instruction, right? So basically, we have an optimizer underneath that would generate different driving routes for the trainee based on the driving problems that the program observed, right? So for example, if the person is really bad at handling complex situations where there are jaywalkers and so on, so the optimizer will generate routes that force the player to go to more places of that sort, right? So that he needs to repeatedly practice how to control a car in that situation, right? So this is the major idea. And of course, in virtual reality, we can track lots of things, right? So we can track the hand motion, and we also can track things that are not easy to track in the real world. For example, the gaze, right? Does the person look at the rear-view driving mirror before making a turn, right? So all these things could be precisely tracked, and then we could compare those metrics with some, the metrics of people who can drive very well, and in order to evaluate how good the person is in a certain skill, and then we can optimize the experience. So this methodology could also be used for other training. For example, we also applied it for wheelchair training, right? Imagine if someone has a car accident and needs to go on a wheelchair, it takes some training for the person to get used to it, right? And in this case, the skills involved, for example, how to rotate orient the wheelchair, right? How to accelerate, how to handle the situation if there are lots of obstacles. And similarly, we are able to generate lots of scenarios for people to practice in virtual reality. And this one is pretty interesting because it involves also a wheelchair that we modify to cope with to associate with the VR experience. And actually, the way we create this prototype is super simple, right? We just bought a wheelchair from eBay, right? And with the trackers we have these days, right? So we can attach a VR tracker to the wheel of the wheelchair, and that way we know how much the wheel has rotated, and from there we can calculate how much the person has accelerated, right? So it's not very hard. The resistance part is a bit tricky, right? Because a wheelchair needs to have some resistance, needs to feel some resistance from the ground. So we need to put on some rough mat that would create that resistance. Of course, there are lots of things we could improve based on this prototype, but it illustrates the basic idea. And we find that people, after trying the experience, they are better at controlling the wheelchairs. Of course, for the evaluation part, we have to ask the person to control a real wheelchair, right, in the real scenario. So we want to see whether just purely based on a virtual training like this, if the person could improve his or her skill, and the answer is yes. So, and along this line, we also work on exergaming. You may have seen demos like this where you can attach a VR headset to a gym bike system, and you will be able to bike in the gym, like a virtual environment. And again, so we modified a gym bike to such that the virtual reality experience could be synchronized with the gym bike in terms of the resistance control, right? So for example, if you're going uphill, you will be able to feel more resistance compared to going downhill, right? So that would give a more immersive feeling. But it's not just about the feeling, it's also about the exercise, right? So we have the algorithm behind that will be able to generate the experience according to the exercise goal, right? For example, if I want to burn a few hundred of kcal of calories, right? So can you generate an experience for me such that if I buy that experience, I will be able to achieve that? And so we have the algorithm to personalize the exercise program. And of course, there's a fun factor here that if you bike, you can enjoy the environment, not just purely biking. So along this line, we also work on virtual reality, augmented reality agents. So these days, we work a lot on AR storytelling. So basically, the idea is that if you have a story, right? If you have a story, by story, I mean like a series of events, right? So like if there is a party here, maybe I get a cup of water, right? And then I grab it, I talk to someone, and then I see a show, and then I dance with someone, right? So given a series of events, which I describe as a story, we will be able to use our algorithm to adapt the story to the environment, right? According to the semantics of the environment. For example, I can throw a party here. I can also throw a party at my apartment. I may throw a party in the hotel, right? So the environment changed, but the story somehow is more or less the same, right? So how can we adapt the story to different environments such that if someone wears an AR headset, he or she will be able to feel the same story? So this is the major goal of the work. So I'm going to skip the details of the algorithm, but I'm going to show you some results that we could achieve. So for example, this is our lab. And so that's the AR view in the through the HoloLens, right? So this is a scenario. So the blue guy is a user. So going at different places, he will be able to see different characters doing different things. And of course, these characters, they are doing things at the right place, right? So for example, the boss sits at the office, right? And the teammates, they all go to the table for the meeting, right? And they also get food from the kitchen, right? So, and then after the discussion, they go to their desks and then work on their stuff, right? So basically, we have a story like this, and we are able to take the lab environment as an input. Of course, just taking the geometry as an input doesn't work, right? We also need to run computer vision algorithms to segment the objects and also to associate the objects with their semantic labels, right? So for example, this is a stage, right? This is a stage, that is a table, that is a chair, so the computer needs to understand all these. But given this understanding, we are able to run the computational design approach formulated around a optimization to populate the objects, the characters of the story to different places, such that the whole experience is smooth and reasonable, in the sense that the objects and the people the people are doing the things at the right place, right? So this is something we have achieved, and at that time, we worked on this about 2 years ago. At that time, we didn't try the ChatGPT, but these days with the LLM, we will be able to even go one step further. So instead of relying on a predefined story, we could even ask the large language model to generate a story for us, right? So for example, hey, ChatGPT, if there's a party happening here, tell me what's going to happen, right? What are the possible events, right? That way, we can have a story automatically generated, and using our engine, we'll be able to populate that story in the environment that the person is in. So we are working along this line. We have a ASIF paper published, not an official publication, but definitely we are working on that, and we have some initial results. So here are more examples, and because the engine is adaptive, it means that it can also understand the user's action to a certain extent, and then being able to accommodate the user's action. For example, if I choose this chair, the other characters are not going to compete with me to get that chair, right? They will sit next to me, right? So we are able to introduce some adaptiveness. And just in case, if you have an empty, empty room like this, using the make it home approach I introduced earlier on, we are also able to generate the virtual objects for this environment in addition to the story, right? So that way you'll be able to achieve more results, even your environment is kind of empty, right? And of course, the virtual reality, augmented reality experience is not limited to virtual characters. You can also have virtual pets realized this way. I'm going to be brief because of the time, but basically, we learned the behaviors of how a cat interact with the environment, right, from some data capture from the real world. And then we will be able to formulate this, again, as a optimization problem, such that the optimizer keeps telling the cat what to do in an environment like this, right? So that, and because the cat is driven by data learned from a real cat, so to a certain extent, it behaves like the real cat. Of course, there are things to improve here. For example, the animation could be more vibrant, right? Because a real cat shows a lot of dynamics, right? But I think this is a good illustration of the idea. And recently, we also moved outdoors. So this is something we have at George Mason. We created an augmented reality dragon that can fly around, right? And so this is a bit different from the indoor scene, because for the outdoor, things are of much larger scale, right? And we need to be able to classify at a more macroscopic way, right? So we need to tell the dragon that, hey, this is a good place for doing what, right? So this is, for example, if it is a shade, then this is a good place probably for resting. If it is water, it is a good place for drinking or swimming. So we get this understanding from annotated data. So we ask people, what do you think, where do you think the dragon would do something, right? So we collect lots of data like this, and we train a classifier such that the classifier, given an environment, the classifier can tell what the dragon probably could do at that place. And then based on that, we are able to, again, use an optimization framework to generate the results of the augmented reality experience. So of course, we did user studies to verify that the experience is realistic and also compatible with the environment. So because of time, I need to wrap up. So I got lots of inspirations from these old games I played when I was a kid, right, in the 80s. And I think we still get lots of inspiration from games. So for example, someone created this video showing what could be the future of Mario. Perhaps in the future, you will play Mario in augmented reality. So I always ask my students, well, if you want to find some interesting problems to work on, so think about you need to create this kind of experience. So what do we still need to do, right? So what is missing here? Is the AI missing? Is the interaction method not good enough? That we still need more improvement, all this kind of thing. So we keep getting inspirations from some interesting applications like this, and that's really fun to explore. And we also work on some commercialization stuff. I have a startup company with my postdoc at the Mason incubator, and we are working on creating some plugins that will be handy for VR, AR developers to do their stuff. For example, we have this plugin that could record a VR section.
Here you can see the VR
including
recording
the
process
human motion
side by side.
and also the
On the left
events
side
that
of the
happened
screen, you can see the
in
real-life
environment.
footage of the recording session. On the right, you can see the screen
And so it's very handy. If you download it, you use it as a Unity plugin, you can have access to the data. And the reason we do this is that because we want to capture the data from the VR section. And then after that, we can run optimization to modify a program. So we also have another tool called the MCMC optimizer, and it's also a Unity plugin. So based on the data that captured, you will be able to formulate some optimization problem and use the MCMC optimizer, which has the algorithms implemented to achieve optimization within Unity. So this is something we have also released, and of course, it's keep improving. So if you have some ideas that you want to collaborate with me, either academically or commercially, feel free to reach out, and we'll be able to provide you with some ideas and support. So I want to thank my team, including my postdoc, my students, for helping with the projects, and also the funding agencies, of course. And thank you very much for having me today. And questions, if we still have time. Yeah.
I was just curious, in the case earlier in your talk where you were having an optimized furniture placement, does the system have any semantic understanding of what the furniture does?
No. So that's something we. So it doesn't have the semantic understanding of the objects, but remember that we provided some examples as the input where the algorithm extract the patterns from. So basically, the semantic consideration was implicitly incorporated in such designs that are created by humans, right? And the machine learning approach just extract those patterns, and by doing that, the patterns already somehow incorporate the semantic meaning, and then the optimizer is able to generate environments that are semantically meaningful. Yeah. Thank you. Any other questions?
For the AR storytelling, I noticed you had like a photogrammetry scan of the entire room, correct? So
Yes.
I was curious, like if a user pulled out the chair and then sat on it,
Yeah.
how would that work? Is it like gonna confuse the program? Is there a way to like
Yeah.
make it understand that this user pulled the chair, so let's move it in VR as well?
Yeah, that's a very great question. So yes, in that work, we assume that you have a pre-scanned environment, and we use the iPad to do the scanning. So if someone changed the environment, like move the chair around, if we don't have the tracking of the object, if we don't dynamically track that, then the storytelling experience will break, because the storytelling experience is assuming the scene is static, right? So we have some other follow-up works that try to tackle that problem, like exactly like you said, like we need to be able to track the dynamic changes in the environment such that the internal representation keeps getting updated. And that way we will be able to generate compatible AR experiences. Yeah. Question?
All right.
Okay.
I think we need to move on. Thank you, Craig.
Thank you. Yep.